Hi, I'm Eddie, and I'll be talking about characterizing and taming resolution in convolutional neural networks, work that I did with my co-authors at the University of Washington, Liang and Ceze. To give some context to this talk, I'll start by mentioning some of the goals and additionally some non-goals. This talk aims to provide examples revealing how resolution exposes trade-offs in computer vision pipelines, uncovering performance pitfalls and proposing solutions for them along the way. On the flip side, this work isn't intended to be a one-size-fits-all recipe for computer vision or deep learning inference. As we'll see, the best decisions for optimization depend on your application scenario, and this includes the problem dataset, domain, model, and hardware, among others. So first, I'll give a quick overview of the history of resolution choices, or the reasons that we've settled on certain defaults that are common today. If you're used to powers of 2 in parameter sizes or shapes in computing, the default of 224 by 224 might seem like a strange choice at first. However, one of the earlier popular instantiations of this resolution was the training recipe of the original AlexNet paper. Back then, random cropping wasn't used. Instead, AlexNet was trained with images that were resized to 256 by 256, with the input to the model itself a 224 by 224 patch of this 256 by 256 image. So the common 224 by 224 input size is really an artifact of this vestigial training recipe. More recently, however, resolution has been given more of the attention it deserves with work like EfficientNet that scales resolution as a parameter just like the architectural parameters of model width and depth. Additionally, the problem of the train-test resolution discrepancy has been attributed to the mismatch of object scales in images at training versus evaluation time. This is because of random cropping's effects on the object scale distribution at training time. To illustrate this last point, consider an input image and 3 potential crops of the input image called small, medium, and large based on the relative amount of area of the original image that they contain. If we take these crops and resize them to the same resolution as shown in the second row, we can see that the number of pixels occupied by or the scale of the objects has changed. Things appear larger in the small crop after resizing, and things appear smaller in the large crop after resizing. If we want to normalize the apparent scale of objects to what is in the medium crop, for example, at inference time, the input resolution of the small crop should be lower and the input resolution of the large crop should be higher. As described in the train test resolution discrepancy, if at training time your model is seeing objects from a certain scale distribution, and at test time it's seeing objects at a different distribution of scales, then this can have a significant effect on the test time accuracy of the model. From this glimpse of the issues arising from the scale-resolution relationship, we can see how resolution can have intricate effects on the model's accuracy. But it gets even more complicated if we consider how resolution affects other components of the hardware-software stack. First, we need to store or receive the input data which scales with image resolution. At the level of the framework, high-performance numerical libraries are needed to support different hardware targets such as CPUs, GPUs, and other accelerators. The compute kernels that comprise these libraries are then themselves usually specialized for specific shapes, which are dependent on the input resolution of the model, as the intermediate shapes of the model are derived from the input shape. Finally, circling back to the issue of apparent object scales, we hope that the model's output is accurate given its test time object scale. Here we summarize the trade-offs and side effects associated with resolution. The first is crop area, or how much of the input image is used for inference. Random crops, which are often very small or use a small fraction of the total image area, are used at training time, and a larger center crop is often used at test time. The second is read size, or the amount of image detail or quality that is stored or transmitted. Note that this property is often informally referred to as resolution, but we can apply more lossy compression to reduce image detail to reduce the quantity of data at the same resolution. Next, we have the inference resolution itself, which together with crop area determines the scale of the object perceived by the model. Finally, the choice of the best compute kernel configuration is associated with resolution because for different input resolutions, the intermediate shapes of the model change, which can change what the best strategy for computation is for each layer. We're showing a toy example here where depending on the input resolution, we might want to change the tiling of the computation. For example, by splitting the 2 loops into 4 loops with an 8x8 tile size. The key takeaway of each of these trade-off spaces is that they introduce pitfalls. For the combination of resolution and image crop area, we've seen that the model must be trained with consideration for the test time object scale, for the best test time accuracy. This requirement means that we have to correct for scale mismatches ahead of time, for example, by fine-tuning the model for a given expected object scale. Instead, we ask if it is possible to correct for scale at inference time, for example, by adjusting the input resolution to the model dynamically. For the relationship between resolution and the amount of data that needs to be transferred or read, the trade-off is a bit more straightforward. Using a higher resolution typically means that more data needs to be read from storage or transferred across the network. However, if we just want to use resolution to match train test object scales, it might be wasteful to use high-quality images or images with fine details. So, can we potentially change the amount of image detail that images are stored or transferred at for each resolution to avoid wasting space or bandwidth with unnecessary data? As for the efficiency of the compute kernels that the model relies on, this is also dependent on resolution, as the input resolution directly affects the downstream intermediate shapes of the model. For each choice of resolution, every downstream operation is a potential source of slowdown if it isn't optimized for the resulting shape. So even at lower resolutions that have a theoretically smaller count of floating point operations, the realized actual speedups may be limited by low utilization if the kernels are not properly optimized for these shapes. And here, the question is, can we recover from this reduced utilization by further specializing the kernels for these operators for each shape? To summarize, our objectives when we talk about taming resolution are, for storage, we want to minimize the amount of storage capacity or network bandwidth that is used by our choice of resolution. For computation, we want to maximize the utilization of the hardware target that we're running on for our choice of resolution. Finally, we want to make this choice of resolution such that we're maximizing the accuracy of our model, that is, by matching the scale of objects at test time to that at training time. Overall, we want to avoid unwittingly making the model worse in any of these trade-off spaces or dimensions. Now, we move to the datasets used for our experiments. First, ImageNet, because that's still the de facto standard. And next, Stanford Cars, which we chose for its strong contrast to ImageNet. It has much fewer examples, and it's a more domain-specific setting rather than being as general as the ImageNet classes. We were also curious if this change in setting would affect the importance of attributes such as scale dependence, as intuitively features relevant for distinguishing models of cars are different from those distinguishing breeds of dogs, which make up a surprising fraction of ImageNet. Next, we move to our approach for minimizing used capacity or bandwidth, calibrating the amount of data that is being read for quality. In other words, we want to separate resolution from the amount of data that needs to be read. For each resolution, we estimate the minimum image quality according to some quality metric like structural similarity that does not sacrifice model accuracy. To do this, we can leverage the training data in each dataset and reserve a small slice for this calibration process to estimate this image quality threshold. At inference or test time, we only read the amount of data that is required to meet this quality threshold. And the only real requirement, in addition to a quality metric, is a progressive image format that allows image data to be traded for quality. Read more data and get a higher quality version, or read less data and get a lower quality version of the image. So one example of an image format that supports trading quality for data is progressive JPEG. Because JPEG images are stored in the frequency domain, we can very naturally get more or less image detail by progressively including frequency coefficients at higher and higher frequencies. The coefficients are grouped into bins called scans, and reading more scans transfers more data, but also refines the image with higher and higher frequency details, boosting image quality. Here, I'm showing a close-up of one patch of the image as more scans are read and displayed, with a cumulative number of bytes shown below. This approach allows us to build calibration curves that map the accuracy loss at each resolution versus the fraction of each image read. In this case, we're showing the curves for ImageNet on ResNet 18 and 50 on the left and on the right. Absolute accuracy change is on the y-axis and the read size is on the x-axis, with each shade representing a different resolution. Each line styling is a different seed to get a better estimate of random variation between the models. Note that while the relative read size is plotted here for illustrative purposes, we calibrate image quality thresholds rather than read size percentages in practice. We can do the same for the CARS dataset as well. Here, the main change we see relative to the ImageNet dataset is that on average, less data needs to be read for images in the CARS dataset to maintain accuracy. We can attribute this to either the CARS dataset having higher quality images, for example, with original images that are on average at higher in resolution, or that fine-grained detail might be less important for the CARS dataset. Now, I'll talk about the ImageNet calibration results as they relate to test time accuracy. Here, we use the ImageNet training set to set quality thresholds to minimize accuracy loss while maximizing the amount of read savings. The top table shows the results for ResNet 18 and the bottom table shows the results for ResNet 50. On the rightmost column, the savings refer to the percentage of image data that was omitted at each resolution, with rows going top down and the columns indicating the relative crop area of each input image. Overall, savings between 5 and 20% are possible at most resolutions without much accuracy loss. Accuracy losses above 0.1% are highlighted in red. We repeat our evaluation with ResNet 18 and ResNet 50 on the CARS dataset. The main takeaway here is that on average, the savings are much higher across the range of crop area and resolution scenarios. Read savings break 20% for most of the scenarios, which together with the results on ImageNet suggests that the amount of possible savings is going to be dataset and application dependent. Next, we describe our approach to compensate for or address scale variation at test time by using a dynamic resolution model pipeline. The dynamic resolution pipeline uses a second model that we call the scale model to pick a suitable resolution to align test time object scales with training time object scales. After the scale model chooses the resolution for inference, the downstream inference task is performed at the chosen resolution. Since scale doesn't require powerful fine-grained classification, we use a lightweight model for this task to minimize the end-to-end overhead. We train this scale model by reserving a subset of the training set of each dataset for this scale task, with a backbone model that has this subset held out. And for our evaluation, we use the backbone that has seen the full training set. This is a high-level overview of our dynamic resolution approach. At inference time, the scale model picks an inference resolution to be used by the backbone model. If additional image data is needed for the chosen resolution, according to the storage calibration that we've seen previously, it is then read and then the backbone model performs the inference task. Next, we evaluate the accuracy of the dynamic resolution approach by comparing it to the default of using a static resolution. Here we're using ImageNet at a variety of crop sizes in an attempt to test the robustness and efficiency of the dynamic resolution approach. The first row of plots shows results for ResNet 18 and the second row shows results for ResNet 50, with each point on the curve showing a different spot in the accuracy compute cost trade-off space. Accuracy is on the y-axis and compute cost is in g-flops on the x-axis. The dynamic resolution approach is a single point on each plot, and we can see that it operates near the apex of accuracy in each scenario, at a comparable compute cost to always choosing the best resolution regardless of the crop size. Next, we move to the same evaluation, but instead on the cars dataset. Once again, each point on the curve shows a different spot in the accuracy compute cost trade-off space. Accuracy is on the y-axis and compute cost and G-flops is on the x-axis. Again, the dynamic resolution approach operates near the apex of each accuracy compute cost curve for both ResNet 18 and ResNet 50. One interesting phenomenon is that the accuracy decrease with high resolution seems to be less extreme than on ImageNet, but more extreme with decreasing resolution, suggesting that how exactly the train test resolution discrepancy plays out is dataset dependent. Finally, we move to the issue of maintaining high hardware utilization with different shapes. Here, our approach is to specialize each kernel as much as possible to recover or preserve utilization. At a high level, we leverage work in automatic kernel optimization such as Halide or TVM to enumerate possible configurations of kernels, for example, different loop tiling configurations, and measure the performance of each configuration exhaustively. Here, we show the throughput results of an auto-tuned implementation of ResNet 18 on the left and ResNet 50 on the right, running on the Intel 4790K processor, comparing the tuned implementation to a library implementation from Intel. The y-axis is throughput in G-flops per second, with different resolutions on the x-axis. While the tuned implementation operates at higher throughput in all scenarios, the important takeaway is that the lower resolution implementations reach a higher proportion of peak throughput when tuned. In other words, we can achieve more of the theoretical speedup usually indicated by the reduction in total floating point operations at lower resolutions with tuning. Now I'll move to the same comparison, but instead on the AMD 2990WX processor. The y-axis is throughput in G-flops per second with different resolutions on the x-axis once again. Here the story is basically the same. The lower resolutions reach a higher proportion of peak throughput when tuned. I'll briefly touch on some of the caveats and alternatives of the results presented so far. At this point, we've established that many of the trade-offs we've seen, especially image quality versus accuracy, is dataset dependent, meaning that per dataset calibration is necessary. Additionally, we focused on situations where per example control flow, for example, choosing a resolution for inference, doesn't add much overhead. But on GPUs, or when batching at inference time is more desirable, other strategies such as batching the scale model's computation might be necessary. Looking forward, one potential source of change is that in the future, as popular model architectures become more and more computationally intensive, it might make sense to use heavyweight metrics for better image quality estimates or scale model predictions. At present, we've had to limit the image quality metric computation and scale model inference to a small fraction of the backbone model's total floating point operation count. Finally, in this evaluation, we fixed our auto-tuning to a limited set of shapes, but as properties such as scale don't change much when changing resolution by a few pixels in each dimension, we could reframe this as a joint optimization problem given sufficient compute resources. That is, could we also choose the precise resolutions to operate at in an online manner rather than fixing them ahead of time for auto-tuning? So, to conclude, the main goal of this work is to show that as resolution is a fundamental hyperparameter of computer vision models, it introduces many intricate trade-offs, many of which are dataset or application dependent. But at the same time, from these intricate trade-offs, we get a rich landscape of optimization opportunities. Thank you, and I hope you enjoy the rest of the conference.